effects. So what this is going to do
We made a
is we're going
cantilever
to
beam
basically
from the
create
bottom
increments
up
that we're
with a
solving that
1
answers
kilonewton
solve.
force on top
This will
of
be
it going
essentially
down.
our reference increment. Now you can see why we want to use 1 as the value for our load. For example, say I have an aircraft wing and I want to see how it's going to handle under aerodynamic loads. I'll put the most basic load on there, say gravity, and then the buckling values I get out would be for how many G's that. So all our loads are applied. So that's everything is checked that needs to be checked for our first run. So now we just solve from current solution. Really quick solution. Simply we're just pushing down a beam. So now if we were to look at the results from this run, it would just be like any other static test you guys have run so far in terms of we're looking at forces and displacements and all of that. We're not going to get any buckling modes out of that run. So what we have to do now is we have to start a new analysis. So we go back, analysis type, we have to do a new analysis, don't hit restart. Eigenbuckling, okay. So now we have eigenbuckling selected. Now we go into our, you'll now see, we selected that, there's new things like expansion pass, load step output. So first thing we have to do is we have to go into analysis options. We're telling the computer what mathematical model we want to solve. Let's say we want to extract the first 5 buckling modes, because sometimes when you're solving problems like this, answers will give you the same mode multiple times just due to mathematics. So while it's a mathematically valid answer, it's not a physical answer in that sense. So let's say let's extract the first 5 modes or so. So we also need to set our shift point for our eigenvalue. And we normally just set that to 1. So what I'd recommend doing if, say, you're doing an analysis where you're going to change designs, is set it up in the GUI like this, go into session editor once you've run it all, and pull it out, because it's a lot easier that way, and you know the code will work rather than trying to type it all up on your own. You're probably going to miss something like the shift or the expansion pass. So now that we've set that up, we go to load step options, expansion pass, single expand, expand mode. So we again set this to 5. Now we have to set our frequency range. And normally what we do for this is we just set it between, say, 1 and a whole bunch of zeros. So what this is doing is just saying that our beam will buckle with a factor between 1 and a whole hell of a lot. So we got that. So now we go to here. Now we start solving. And because it's a very simple problem, it solves quickly. So now we're no longer going to really care about the force, displacement, data, anything like that. We're going to care much more about the modes. So to get those, we can go into General Post-Proc, List Results, Detailed Summary. Here we go. Here are our buckling modes. So the reason why I put it in 5 but only got 3 is because it solved for the same one twice. So our first buckling mode is at 143.93. Our second one is at 1294.7, and our third is at 392.6. So when we're going to go in and actually look at our results, we only need to look at 1, 3, and 5. So an important thing to remember about buckling is it's what's called a stochastic event, which basically means random. So you can always design to have a structure buckle in a certain direction, But if we're doing something like this, I don't know if it's going to buckle in the X direction. I don't know if it's going to buckle in the Y at 45 degrees between the two. That is purely just, and it's going to be different every time. As you guys probably learned in 322, sometimes it buckled to the left, sometimes it buckled to the right. We can control that through changing the value for moment of inertia, but that can only do so much. So remember that when you're designing that buckling, we can't really control direction. So to look at the different modes, let's go to read result. So first set, let's just look at the deformed shape. And where's that both? There we go. So that's our first mode. It is what we expected. You see it's just got kind of the curve comes down to here. Because it's fixed, it's L over 2, so if you remember, it's kind of like, then this is mirrored on the other side of the boundary condition. And so what you'll see is we have a factor of 143.925. So that is the amount of force it would require to buckle this beam originally. So that's why we use 1, because it's just 1 times 143. So 143 pounds is the first buckling mode. If we use 2, then we get like 71.5. So whatever you set that as is going to be your multiplier times that. So let's look at, I want to go to our third set. There we go. This is our essentially our second buckling mode, even though it's our third subset, it's second. And you can see it's just got that kind of classic half a trig function wave to it. And then our third buckling mode that we extracted. See, computer doesn't know which way solved. So we go here. We can see it's kind of got a nice S shape to it, which is what we expect from our third buckling mode. So an important thing about looking at solutions like this is realizing what's valid, what's not valid. You know, what does the mechanics of materials tell us? What does the differential equations tell us? So a big part of learning to do structural analysis is learning to do stuff like this. So that's kind of an intro to buckling. So how about we start doing plate buckling next, because that's kind of the logical progression. We've done a beam, let's do plate. So if you guys just want to come up with a 1 meter by 1 meter by 1 millimeter plate, say out of aluminum, let's find the buckling load if you only press down on one edge. So if you guys want to start coding that up, if you have any questions about it, solve, and let's find out what the first buckling mode is. So if you have questions, just flag me down. This will also give you guys a chance to get the session editor code out of there. So I'd recommend taking that and emailing it to yourself, and that way you'll always have it. Because it might not be in this class where you do a buckling analysis, but it might be in, say, 462 or 426. And you can valid, so anything between 0 and 1 is also valid. Now you can see, kind of as we expected, that the blade buckles very similar there. It's a very similar pattern to the way that the bead buckles. That's because it's essentially undergoing the exact same type of mathematical manipulation that the bead buckles. So the final kind of buckle is biaxial. Pretty much the same. So now we've gone from uniaxial to biaxial loading. Very rapid drops in our ability to carry load in terms of how quick the load is. We've gone from 1.6 to 1.15, so about a factor of half almost.
Yes.